So before we begin lesson 3 for chapter 3, powers and exponents, I would like you to take a minute and look at the front page of your notes on the back of your outline. And it has some space for you to create a cheat sheet for all of the different exponent laws we're going to be talking about. You can either choose to do them all at once, or you can choose to do them kind of as we go through your notes. All of the different exponent laws will be outlined in your notes, but it's good to have them kind of all in one place as a quick reference and a cheat sheet. I will be expecting you to know these by the end of grade 9, but as we're just getting started, it's good to have them as a reference sheet to help you begin to remember them. So I would recommend pausing the video and filling this table in if you would like to do it all at once, or once you're done your notes, go back and after this lesson you'll be able to fill in the first 2 powers laws. So product of powers and quotient of powers. Okay, so here's our outline for today. And so we're still going to keep working on demonstrating powers with integral bases and whole number exponents as repeated multiplication. And we're still going to work on using repeated multiplication to represent as powers, but we're going to take this one step further. And so by the end of this lesson, we should be able to show when you have repeated multiplication of the same base and they're being multiplied, we should be able to use repeated multiplication to help write this base as a single power, and that's going to show us the product rule. And we're also going to look at using repeated multiplication of the same base and using division to help prove and show what the quotient rule is. So just as a reminder, let's write these out as repeated multiplication. And so we want to be looking at examples where we have the same base being multiplied. So in this example, our base is 5, and in this example, our base is 5 again. So we have 5 cubed times 5 to the 4. Okay, so we could solve those individually. I could type 5 cubed in my calculator, and then 5 to the power 4 in my calculator, and then times those answers just by following BEDMAS, especially now that we're using our exponents. But I want to just try writing it as a single power. And so I have a base of 5, and 5 is being multiplied 1, 2, 3, 4, 5, 6, 7 times. So this is actually the same as saying 5 to the power of 7. And you hopefully have realized when we get to 7th powers that those are kind of big numbers. So we'll just represent it as a single power instead of multiplying it out. When we look at the second example, again, we have the same base. So we have a base of positive 4 and a base of positive 4. So we have 4 squared times 4 to the power of 4. And that's the same as having 4 being multiplied 1, 2, 3, 4, 5, 6 times. So that's 4 to the power of 6. So hopefully you noticed a pattern that we had 3 5s, and then we had 4 5s, and 3 and 4 is 7. In the second example, we had 2 4s, and we had 4 4s, and 2 and 4 is 6. So the product rule, or the pattern of the product rule, is that if you have the same base being multiplied, the exponents are added. So when you have the same base being multiplied, the exponents are added. So we're going to look at these 4 examples, 5 examples below, and try to use this product rule. Again, the first thing I'm checking is what is the base. And so we have a base of 4, a base of 4. So we have the same base being multiplied. That means I can add the exponent. So this is the same as 4 to the power of 8. And if you're not so sure about this, write it out as repeated multiplication just to double check and prove it to yourself. In example B, again we have brackets, so the negative is part of the base, so negative 5 squared times negative 5 cubed. We have the same base being multiplied, and so we add the exponents. I hope you notice that the base hasn't changed at all. So negative 5 to the power of 5. Okay, third one. There's no multiplication sign in between them, but we remember that if we have two brackets stuck together or a number stuck together with a bracket, it does mean that they're being multiplied. And so we have the same bases being multiplied, negative 3 to the 7 times negative 3 cubed. And so we can add the exponents, and we get negative 3 to the power of 10. In these two examples, it's really important you keep the brackets around your base, because negative 3 to the power of 10 has a very different value than negative 3 to the power of 10 without brackets. Remember, in this second example, only the 3 is to the power of 10, and so this second example would have a negative answer, whereas this first example would have a positive answer because it's a negative base with an even exponent. So making sure you're really aware of when and where your brackets go. Looking at D. First thing we try to investigate is, do we have the same base? In this example, we do not have the same base. And so because the bases are not the same, we cannot use the product rule. So other than finding out what is 6 to the power of 5 times 4 to the power of 2, we really can't do much else. And so the example asks us to put them as a single power. Well, this is it. That's as far as we can go. We can't reduce any further using the product rule because the bases aren't the same. Right. When we look at E, so remember we were saying if we have a number outside a bracket or two brackets side by side and there's no operation being shown, that it is a multiplication example. So this is 100 to the power of 4 times 100 to the power of 8. I can almost guarantee that if you type this in your calculator, and you should try it, that it is not going to give you something that you are familiar with. And it's probably going to be something like 1e and then a big number, or 110 to the power of a number. And so, anyways, we'll get there. Either way, in both cases, in both 100 or 100 in the brackets, the base is the same. And so because we have the same base, we can add the exponents. Because the base is positive, it doesn't matter if we use the brackets or not. It's kind of a personal preference. So you can either leave them off or you can put them on. As long as the exponents stay outside the brackets like that, then we're okay. And so we get 100 to the power of 12. And if you put this in your calculator, you would get 1.0 times 10 to the 24. Or you might see 1e24 in your calculator. What that means is the decimal place needs to go 24 times to the right. So there's actually 24 places of zeros in behind that number. And this is what we would call scientific notation. And so we use scientific notation when there are numbers like this, where there would be 24 zeros behind. Rather than showing all those 24 zeros, which are just zeros and don't really impact the value, we can write it in a condensed format of 1.0 or 1 times 10 to the 24. We can also use scientific notation to show very, very small numbers. And so we might have something like, oops, 1.0 times 10 to the negative 24. So remembering that negative tells us the left direction, this is saying that the decimal place is actually 24 times to the left. So there are actually a bunch of zeros in front of this 1. So this is a very, very tiny value. So that's, you might see scientific notation, especially going forward for some of our examples, and especially going forward in science when you're looking at either really small organisms or maybe distances in space, that kind of thing. Okay. Hopefully you've noticed that these examples are a little bit different than the last examples. These examples are division examples. And so a reminder that the answer when you divide is called the quotient. And so we're going to set these up like division. And I actually want to set them up using fraction division. So I'm going to set them up this way. 2 to the power of 6 over 2 to the power of 2. So that's going to look like this. 2 times 2 times 2 times 2 times 2 times 2 over 2 times 2. So hopefully you remember. If not, I'm going to remind you that when you have something divided by itself, you get a value of 1. Okay, so 2 divided by 2, that cancels out to 1. 2 divided by 2, that cancels out to 1. So on the bottom, we end up with 1 times 1. And on top, we have 1 times 1 times 2 times 2 times 2 times 2. So on the bottom, we've basically canceled everything out of value. So we just have 1. And on top, we have 2 times 2 times 2 times 2, or 2 to the power of 4. And 2 to the power of 4 divided by 1, dividing by 1 gives us the value itself. So just 2 to the power of 4. When we look at the second example, we're going to write it out the same way. So negative 5 is our base to the power of 7 divided by negative 5 to the power of 3. Both of our bases are the same, so we're going to write it out as a repeated multiplication. Negative 5, 2, 3, oops, 4, 5, 6, oh, I got to put 1 back at the beginning again. It's 7 over negative 5 3 times. 1, 2, 3 times. And so again, I'm going to do some canceling out, because when you divide a number by itself, you get a value of 1. So there's a value of 1, there's a value of 1, there's a value of 1. And we get left with negative 5, 1, 2, 3, 4 times, so negative 5 to the power of 4 over 1, so negative 5 to the power of 4. So did you notice the pattern? Well, in the first example, we have 6 divided by 2, and we ended up with 4. In the second example, we had 7 divided by 3, and we ended up with 4. I hope you noticed that the pattern is subtraction. So this is our quotient rule. When you have the same base being divided, the exponents are subtracted. When you have the same base being divided, you subtract exponents. So taking a look at these examples. 5 to the power of 7 divided by 5 to the power of 2. In both cases, the base is a positive 5. They're separated by division, so I'm going to subtract the exponents. If this seems a bit weird to you, I want you to stick with doing the cancel out method for you, if that helps you see it a little better. And so we end up with 5 to the power of 5. When we look at B, we have a base of negative 6 and a base of negative 6, so the bases are the same. They're separated by division. and so we subtract the exponents. So we get negative 6 to the power 4. When we look at C, we have a base of 3 and a base of 7. The bases are not the same, so the quotient rule does not apply. We cannot write these as a single exponent because the bases are not the same. The best we could do would be evaluate what is 3 to the power of 4 and what is 7 to the power of 8, and then divide that fraction. But we'll leave it at that. Last example, 4 to the power of 8 divided by 4 to the power of 7. We have the bases that are the same, so we can subtract the exponents and we get 4 to the power of 1. And 4 to the power of 1 is just 4 one time, so just 4. I'm going to leave you with one thing to think about before we end this lesson. I want you to think about what would happen if these were changed, the order was changed. So if in this first example, what if it was 5 to the 2 divided by 5 to the 7? What would that look like? Or what would negative 6 to the power of 5 divided by negative 6 to the power of 9? What would that look like? Or on this last example, what if it was 4 to the power of 7 over 4 to the power of 8? We're going to discuss this at the start of tomorrow's class.